of a curve that starts at t is equal to a and ends at t is equal to b, then my formula for arc length is the integral. Now, one version of this is that we're going to add up all the little arc lengths across our curve, and so this is the shorthand form. And the reason that I'm using this format here is that you'll see this a lot in Calc 3. Okay? You'll see these DS's integrating across a curve rather than having numbers on the top and the bottom. So the idea is that if you have a curve, there it is, we're going to break up the curve into little pieces, and here is your little section of that curve, that's ds, and then you want to add up the ds's all along the curve, and so that's what the integral sign is saying. Now that wasn't overly useful, but what was useful is we rewrote this formula as the integral of the square root of dx over dt squared plus dy over dt, thank you, squared, and then a dt at the end. And this was actually more useful because now, since we're looking in terms of time, or in terms of the parameter t, then if our particle starts at time t is equal to a, then that's our bottom boundary. And if the particle ends at the other end of the curve at time t equals b, then that's our top boundary. And so this is actually a much more useful formula for us to work with. Are there any questions on either the homework or any of the practice problems? Ben?
I was actually just going to ask if the left side of the c to nothing ds would be considered improper or not.
Oh, so this c is not actually a number.
Right.
This is saying when we put something down here where this whole curve is called c, then this says we're going to integrate over the curve c.
Okay.
And so that's just a slightly different notation, but it's saying it's not improper or anything like that.
Okay.
Charlie?
Number 47.
Good. Number 47 out of 13.
90.
90. What did I say? 90. 902, number 47. Okay. So find the distance traveled by particle as t varies in the time interval. And then it asks us to compare with the length of the curve. Okay, in number 47, we have x equals sine squared t, and y equals cosine squared t. And then the t boundaries that they give us are t goes from 0 to 3 pi. Okay. So, Shiloh, what were your thoughts on this problem?
I found the derivatives and plugged it into the equation.
Okay.
And then I approximated the integral, and then I looked to realize that.
Okay. So let's take a look at a few things. First one is, may I borrow your calculator? I seem to have not brought mine today, and I'd like to draw a picture of what this thing looks like. t. And I actually want to square that, so I think the best way for me to square that is to start with parentheses and write sine of t, end the parentheses, and then square. And then for my second one, for y, I want to look at cosine of t and square that. And I'm actually going to start, just for kicks here, with zoom standard. And this is a really silly looking picture because you can barely even see it, right? I mean, you've just got this little diagonal line down there. So I'd better zoom in a little bit. And by the way, this makes sense because, I mean, sine squared and cosine squared, neither of those values are ever going to get any larger than 1. And so my x and my y are never going to be any larger than 1. So let's zoom in a little bit. We'll change our window. Our x minimum will have be -1, x maximum +1. Our y minimum -1 and our y maximum +1. And as far as our t values go, since we're interested in t starting at 0 and going to 3 pi, I'll go ahead and type that in right away, and then hit graph. And so what I end up getting is a picture that looks like a diagonal straight line. All right, now in terms of this curve that I have here, I want you to look carefully. If I type in y equals, and I change this to that little circle symbol, watch carefully what's happening with this particle. Drops down, it bounces back up. So that particle is moving along that path. It repeats its time over and over on that path. And so if we look carefully at the trace function, as t goes from 0, okay, now we're down here at the bottom, and t is looks like roughly pi over 2. And then we get back up to the top. So it takes from 0 to pi for the particle to go down and then back up. And so that should happen 2 more times. So here we are now at roughly 2 pi. And then we have a 3rd time as well. All right, so there's something funky going on here. And before we get to the actual calculation of the integral, there's 2 separate questions that are happening here. One is, what is the arc length of this curve? Well, if I want to figure out arc length, well, I don't want to count the curve 6 times over, right? I want to take the amount of time it takes to go and travel and cruise along that curve exactly 1 time. And so in this particular case, for the arc length, we only want 1 time across our curve. And so 1 time across our curve is going to look like t going between 0 and pi over 2. But the distance traveled by that particle is actually going to be 6 times that amount. And so our distance traveled ends up being 6 times the arc length. Are there any questions just about clarifying between distance versus the arc length before we set up any sort of an integral? The distance traveled, I can integrate from 0 to pi over 2 and then multiply that by 6. So here is your calculator back. Thank you for letting me use it. And so in terms of our example for the arc length, our arc length is going to be the integral from 0 up to pi over 2 of the square root of dx dt squared plus dy dt squared, all of that into the square root and then a dt at the end. So now these functions are squared functions, so I have to be a little bit careful. Since x is equal to the sine of t squared, then dx dt, I have to use the chain rule on this guy. So I've got 2 times the sine of t times the derivative of the inside, which is cosine of t. And then for y is cosine of t squared. So dy dt looks like 2 times the cosine of t times negative sine of t. Alright, so when I square these things and I calculate, and I write down my arc length integral, I end up with the integral from 0 to pi over 2, and then dx dt squared looks like 2 sine of t cosine of t quantity squared, plus negative 2 sine of t cosine of t squared. Take the square root of all of that, and a dt at the end. Okay, are there any questions about setting up that integral? Alright, if all I wanted to do then was to figure out what this value is, I could type in this integral into my calculator and come up with a numeric value. If I wanted to make my life a little bit easier before doing that, then what I might do is to try and simplify under the square root. And so under the square root, I end up with 4 sine squared t cosine squared t plus another 4 sine squared t cosine squared t. And all of that is happening under the square root. And I have a dt at the end. And that negative up there cancels with my square, so that's legit. And then I can combine these terms, and I've got the integral from 0 to pi over 2 of the square root of 8 times sine squared t times cosine squared t dt. Alright, is there anything else I can do here to simplify any more? Yeah, so the next question is it legitimate to cancel the square root with each of these squares? And the answer is absolutely yes. And the reason is because these are all multiplied together. If there had been addition in there, then that would have been illegal algebra on your paper. Okay, so totally legitimate to split up these terms and take the square root of each term individually. And so we end up with the integral from 0 to pi over 2 of the square root of 8 times sine of t times cosine of t, and then I have a dt at the end. Now that I've done that, yeah, I can take this square root of 8 and pull it out in the front. So I've got square root of 8 times the integral from 0 to pi over 2 of sine of t times cosine of t dt. All right, any questions about this integral so far? This is a really good review question also, once we get to this point. So at this point, take a look at that integral, and then turn to your neighbor and tell your neighbor what integration technique you would like to use on this particular integral.
Well, in my purely amateur opinion,
All right, anybody agree with your neighbor? Ben, what did your neighbor agree on?
I was doing you said,
Okay, and so what would you like your U to be?
just sine t is fine.
Okay, yeah, it doesn't really matter which one we allow to be the U because the derivative is there either way. And so let's go ahead and let U be equal to sine of t, in which case du over dt is cosine of t, which tells us that dt is equal to du over cosine of t. And so in terms of our integral, we've got square root of 8 out in the front. We've got our integral of u times cosine of t times du over cosine of t. And I'm going to put asterisks for my bounds because I haven't made a decision about whether I want to have u or t bounds. So I've got square root of 8 times the integral of u du evaluated between my two boundaries. So life is good, I canceled all the t's. My two options, number one option is that I can change these into u boundaries and then take my antiderivative and plug these values into my antiderivative. Or I can leave these as t boundaries, do my antiderivative, turn back into t's, and then plug in the boundaries. And I think today that's what I'm going to go ahead and do. So here we've got our square root of 8 times u squared over 2 evaluated on our boundaries. And I'm using asterisks because I want to remind myself that I absolutely positively do not want to plug 0 and pi over 2 in for u, because those are t values and right now I have u's. So now I've got to go back to my t, and so I've got square root of 8 over 2, and then u is sine, so we've got times sine squared t, and we're now going to evaluate between 0 and pi over 2. Alright, so we end up with root 8 over 2, and then we have sine squared of pi over 2 minus sine squared of 0. And so sine of pi over 2 is 1. Yeah?
Don't be.
Oh, okay. Sine of pi over 2 is 1. 1 squared is 1. Sine of 0 is 0. 0 squared is 0. So we end up with root 8 over 2 times 1 minus 0. And so we end up with root 8 over 2. So this is an okay final answer. But one thing that you might have noticed when we drew the picture was that the arc length that we had was the hypotenuse of a triangle whose sides were 1. So what would we expect this hypotenuse size to be? Yeah, this should be a square root of 2. So this number would also going to be square root of 2, and it is. If we rewrite root 8 as square root of 4 times 2, then we can have square root of 4 as 2, so we have 2 root 2 over 2, and the 2's cancel, leaving us with square root of 2. Okay, so this tells us that the path, this arc length, the length of the curve, is square root of 2 units. Now in terms of the picture, the funky thing that's happening is that particle goes down and up and down and up and down and up. So our distance traveled is 6 times that, and the arc length itself is square root of 2.
And then in these questions, will you ask about displacement?
I will not. So this arc length is strictly about not displacement but distance traveled. If you want to know displacement, all you would need to do is plug in t equals 0 into the original parametric curves, and then t equals pi over 2, and measure the distance between them.
Okay. And then just for review's sake, where you have your asterisk there, if you were to go the u bounds, you would plug in your original bounds into
Wait, hold on a second. So you guys, this might be a good question because I know a bunch of people have been thinking about this recently. So go ahead and re-ask your question.
So with that point, if you decided to go the u bound route,
Yes.
you would take your original bounds, plug them into u equals sine of t, to
Correct.
get new bounds, and then you would substitute just those values in over u squared divided by 2?
That is correct,
Okay,
yes.
and then it would technically be the same answer.
And if you think about these bounds, when t equals pi over 2, u is going to be equal to 1. And when t equals 0, u is going to be equal to 0. So your u bounds would be 0 to 1, which is going to give you exactly the same thing as if you plug in 0 and pi over 2 in for t. Other questions about this example? Charlotte, did that answer your question? Cool, so I'm glad you asked about this one because I specifically had this in there because it is a very strange looking question. And the moral of the story is, whenever we're talking about arc length, then what we need to think about is, okay, the picture that we've drawn, are we transversing across that picture exactly once, or are we repeating ourselves across that path? And so to figure out arc length, you want to just traverse the path exactly one time. So exactly from the top corner down to the bottom corner one time. And then if the particle repeats itself, then our distance traveled has to accommodate for that by saying, okay, how many times are we moving across this path?
And that's how you get that little circle goes around,
That's right, yes.
and it goes 6 times. So then
That's correct.
6 times that answer.
Yes, so a concluding comment on this one, if we were summarizing this particular problem, would be that the arc length is equal to square root of 2, but the distance traveled is equal to 6 square root of 2, because the particle traveled along that path 6 times. And the only clear reason that we know that is by drawing the picture and looking at it. Okay, other questions or comments? Okay?
So would you get a different answer if your integral went from 0 to 3 pi?
So if we went from 0 to 3 pi,
Isn't that the initial range for t?
so if we took our initial range from t, then the integral from 0 to 3 pi of the square root of all that stuff, which turns into, if we simplify it down to the integral from 0 to 3 pi of square root of 8 times sine of t times cosine of t dt. And then we do our antiderivative, and our antiderivative would look like this, and so then we plug in and we'd end up with, let's see here, square root of 8 over 2 times sine squared t evaluated between 0 and 3 pi. And so then when we plug in these values, we've got sine squared of 3 pi minus sine squared of 0. And sine of 3 pi is 0. It's on the left side of the x-axis. And sine of 0 is also 0. And so we'd actually end up with a net value of 0, which Shyla, I'm guessing is what you came up with when you originally did the problem, maybe.
Yeah, I did it like the previous problems.
Okay, yeah, so this idea with the arc length is this asterisk on these problems, that this idea for arc length works as long as you're not going back over the same particular curve. And so when that happens, I mean, in the end, that particle went from the top point, it went down and up, down and up, down and up, it ended where it started. And so because of that, life got messed up. And also because, well, why else did it get messed up? Yeah, but the example we did last class in the circle and ended where it started, we've still got the circumference of the circle. Let me think about that a little bit more. Why do we get 0 for this one? All right, other questions about this example? John?
I'm kind of curious, so if you do the display, or not, sorry, if you take the integral of it for like the original length for the whole distance anyway.
Yep.
Is that accounting for the displacement then at that point? Or is that what you're trying to figure out with the circle over here, since it's starting and ending at the same?
Yeah, so that's,
But since it's on the same path, is that what is causing that as opposed to where the circle, there, it's in different quadrants the whole way around?
Yeah, and that's the question, so I'm gonna think about that during our 10-minute break, I don't have an answer for you yet. Alright. Let's take a 10-minute break here, when we come back, okay?
And I think it's mostly just, I got everything, but kind of just the integrating after figuring it all out. So, I mean, you can plug it in your calculator and get it pretty simply, but I didn't think it really wanted that.
Okay, so there are a couple of things that we were gonna do with these, with the arc length of the curve. In terms of calculating the final values, when I'm asking you to set them up, or when I'm asking for this on the exam, I'm gonna have separate questions for evaluate the integral versus set up the integral, mainly because I don't wanna have to grade incorrect integrals and how those are integrated. So in terms of in terms of our applications, I'm gonna be asking you to, if I ask you to evaluate it, it's with your calculator. But we can definitely look at it if you'd like to, or why don't we take a look at it and sort of see what kind of strategy we might get for this. Okay, so this is number 39 in section 9.2, and we have x is equal to t over 1 plus t, and y is equal to natural log of 1 plus t, and then t is going to go between 0 and 2, and our job is to find the length of the curve. So it's kind of nice if you graph this, but we'll just go ahead and work with the calculations. And so when you calculated dx over dt, which we're certainly going to need, what did you end up getting for that?
1 over 1 plus t squared?
1 over 1 plus t, the quantity squared?
Yeah.
Okay. 1 over 1 plus t squared. And so when I'm thinking about this, I'm thinking about the quotient rule, right? So I have low d high minus high d low, draw the line and square below. Okay? And then for dy dt, what did you come up with for that one?
1 over 1 plus t?
1 over 1 plus t. Okay, cool. Alright, so these are my derivatives, so my arc length is going to be the integral from a to b, which is from 0 to 2, of the square root of 1 over 1 plus t squared, plus 1 over 1 plus t, the whole fraction squared. I need to take the square root of all of that and then have a dt at the end. Okay, so this is our integral and it is all set up. Are there any questions about setting up that integral?
You just find the derivative and then put it under the square root.
Yep, find your
Square that.
derivatives, square them, put them under the square root, and there is your formula for your arc length. Okay, so now if we want to evaluate this integral, well, some things that we might have to work with here. We have integral from 0 to 2. I've got 1 over 1 plus t quantity to the 4th, plus 1 over 1 plus t squared, and the square root of all of that. Erin, what were your thoughts on this one?
Factored out 1 over 1 plus t squared.
Okay. So you've got the integral from 0 to 2 of square root of 1 over 1 plus t squared times 1 over 1 plus t squared plus 1. Okay, and then a dt at the end. Seems reasonable so far. And then this 1 over 1 plus t squared, we can pull that outside the square root and take the square root of that. And so we've got the integral from 0 to 2 of 1 over 1 plus t times the square root of 1 over 1 plus t squared plus 1 dt. Okay? So what are we going to do next?
That's kind of where my memory lapse hit, and I wasn't exactly sure where to go from there.
Alright, this is a really good question. So where are we going to go from here?
Doesn't,
Can we get rid of the radical by raising them to the powers of 1/2, or would that just open it
Well, so we could put this entire expression raised to the 1/2. It's like one possibility, that might do something for us. And if we wanted to completely get rid of that square root, then we'd have to combine those terms inside. So we could find a common denominator, I don't know if that will help us, it might. Try it out. Integral from 0 to 2 of 1 over 1 plus t times the square root of 1 over 1 plus t squared plus 1 plus t squared over 1 plus t squared dt. And then we can combine these like terms. The integral from 0 to 2 of 1 over 1 plus t times the square root of 1 plus 1 plus 2t plus t squared over 1 plus t squared dt. And so we've got the integral from 0 to 2 of 1 over 1 plus t times the square root of 2 plus 2t plus t squared divided by 1 plus t squared dt.
Could you just foil the bottom and then,
Yeah.
and then just do a, so then it would just,
You just evaluate them separately to do that?
Yeah, that's what you do. Take the-
Well, I cannot evaluate these separately because I have times in the middle here, and whenever I have multiplication, that's gonna be an illegal move. If it was a plus sign or a minus sign, I can separate them, but with times, I cannot.
You know what I did was, I expanded both of them before you clear up there at the first argument step there.
Way up here,
Uh-huh.
okay,
Before I put it under, I expanded the whole thing to t squared plus t, 2t plus 2, and all of that was over 1 plus t to the 4th. So I didn't factor out the 1 over 1 plus t. I never factored that out.
did it get you in a better place?
Yeah, because then what I wound up with was the square root of t squared plus 2t over 2, plus 2 I mean, all over 1 plus t to the 4th, and then I took the square root of the top and the bottom separately. So what I wound up with was the top is the square root of t squared plus 2t plus 2,
Okay,
all over 1 plus t squared.
okay, so if we were to bring that back in, then we'd have t squared plus 2t plus 2 over 1 plus t to the 4th.
And then take the square root of each one of them
Uh-huh.
separate.
And did that help you along the way?
Yeah, because then I took the radical off the bottom, so it's just 1 plus t squared,
Okay.
and then I did a u sub, where u is 1 plus t.
And when you did your u sub, you let u be 1 plus t,
Yeah.
and then your du over dt is 1, right? So dt will du. So we've got an integral here, dt at the end. Alright, so you have a u squared at the bottom. What about this top part?
It was u squared plus 1,
Okay.
square root of u squared plus 1. Because use 1 plus t.
And so we've got the integral of the 2 plus 2t plus t squared over u squared du. And so with these t's up here,
Yeah, with that u sub up there, that becomes u squared plus 1.
alright, so if our u is equal to 1 plus t, then t is equal to u minus 1, which means that up here, we've got the integral of the square root of 2 plus 2 times u minus 1 plus u minus 1 squared divided by u squared du. And so if we clean this up inside, we've got 2 plus 2u minus 2 plus u squared minus 2u plus 1, square root of that, divided by u squared du. And then we can clean up stuff inside. Plus 2u minus 2u plus 2 minus 2. And that leaves us with the integral of the square root of u squared plus 1 divided by u squared du. What did you do from there?
Changed the bounds and just solved it out. The bounds went from 2 to 3.
Okay, so if your original bounds went from 0 to 2, then when t is equal to 0, u is going to be equal to 1. When t equals 0, u is equal to 1 plus 0 is 1. And when t is equal to 2, u is equal to 1 plus 2, which is 3. So our bounds are going to go from 1 to 3. So integrating this thing still seems like a bit of a challenge. Let's see. What could we do with that thing? Ignore it? Throw it back in the dark alley.
Could you raise it to the 1/2 and then just subtract the exponents?
That integral would throw you back into the dark alley.
Okay, so maybe, don't throw me back.
Oh, no, I meant the.
I understand what you meant, I'm just teasing. Okay, so, alright, so if we had not simplified this denominator, then this really would be the square root of u to the 4th, right? This denominator here, if I write that as square root of 1 plus t to the 4th. And then here, this would be square root of u to the 4th. And then this one is square root of u to the 4th. And so we have the integral from 1 to 3 of, I can not split up the square root and have u squared plus 1 over u to the 4th. And then I've got my integral from 1 to 3, and I've got square root of u to the negative 2 plus u to the negative 4. I'm not sure if that helps me very much. No. I don't like this problem, man.
Maybe we're supposed to use the calculator.
I was gonna say, is this the
Get
point
one.
where you bring up the calculator?
Now
We're
this,
not there yet.
now this is when you look at the solutions manual.
Yes, yes. But then the solutions manual just confuses you further and then you push it after. Where the solutions manual says take out your calculator.
Does it ever actually say that?
I hope so.
Some of the questions, they just skip a bunch of test steps and just use finance.
This idea here seemed very promising to me. I was pretty excited about this u equals 1 plus t idea. And I like that it got us down to here. And even if this is u squared, I still like that.
Use a trig sub.
That seems like a reasonable idea. So why would it, what made you think about a trig sub? You cheated? Well, what would you, had you not cheated? Had you not cheated, what would make you think about a u sub? I mean, a
Square
trig sub.
root of u squared plus one, that's, could be tangents.
Yeah, this is an x squared plus a squared form. And so at this point, I was hoping we could avoid that by doing something like this, but I don't think so. All right, it's all yours.
Good luck.
All right, so Dano's suggestion of this u sub here was pretty darn clever. And so great, so we've got our u sub. Things cleaned up in an unexpected way. And then we get over here and it makes us want to cry a little bit. And then we look at it a little longer and say, all right, well we've got an x squared plus a squared form with a square root over it. This is a trig sub. And so that's where we go from here. Oh.
That won't be on the exam.
Please.
Well, a trig sub could be on the exam, or a set up the integral, or well, actually, it's totally wrong. So set up the integral to find the arc length, or something, part of these, but not all of it. So, yes. I will not ask you to set up this particular integral in the exam. This is a bonus one to solve. Okay. All right, Aaron, is that semi-answer your question?